Every detail in this story comes from real scientific research and observation. There is a machine falling. Not drifting, not floating, falling nose first into the atmosphere of a planet 11 times wider than Earth at 31 kilometers per second, and it is on fire. It chose this. It was built by human hands, launched into darkness 20 years before its end, and it flew for 7 years before it even arrived. It crossed the orbit of Venus twice. It passed the moon at 68,000 kilometers. It slingshot around Jupiter, and when it finally reached Saturn, it stayed for 13 years. 13 years. In that time, it passed through a ring gap no spacecraft had ever entered. It dropped a probe into the atmosphere of a moon. It flew within 25 kilometers of a world that should have been dead, and found warm water shooting into space. Tonight, you are going to live all of it. You are going to feel the slow crawl of 7 years through empty space. You are going to feel the engines fire for 96 minutes at Saturn's edge, or die trying. You are going to descend through the orange haze of Titan. You are going to hover over the south pole of Enceladus, while water vapor rises around you at 400 meters per second. And you are going to be there at the end. September 15th, 2017. You will feel the heat building on the hull. You will transmit as long as you can. You will send every last measurement home before the signal stops. The spacecraft does not grieve, but the people watching the screens in Pasadena, California, they did. There is a moon the size of Arizona, with an ocean hidden 40 kilometers beneath its ice. Nobody knew. Then Cassini flew over the South Pole at 25 kilometers altitude, closer than a commercial aircraft flies above Earth, and the instruments detected water vapor, not ice, not frost. Liquid water, moving fast, shooting upward through cracks in the surface at 400 meters per second and erupting into space. Warm water, salty water, water containing hydrogen and organic molecules. On a moon that should be frozen solid, something is keeping the interior warm. There is a world called Titan where it rains. Not water, methane. Liquid methane falls from orange clouds onto a surface of water, ice pebbles, rounded by ancient flows, collects in rivers, drains into lakes, and evaporates back into a sky thicker than Earth's. In 2005, a small probe dropped from Cassini's side fell through that sky for 2 hours and 27 minutes, transmitting every measurement it could, and landed softly on a surface no instrument had ever touched. It survived for 72 minutes on the ground before its batteries died. 72 minutes of data from the surface of another world. There is a ring gap 2,000 kilometers wide between Saturn's cloud tops and its innermost ring. No spacecraft had ever flown through it. In 2017, Cassini did, 22 times. Flying blind through a space that had never been sampled, collecting dust particles on its instruments, measuring magnetic fields that had never been directly measured, tasting Saturn's upper atmosphere. 22 times. And then the fuel ran out, and the engineers made a decision. They aimed it at the planet. Not to crash, not to fail, to go in deliberately, transmitting until the last possible second, returning data on the composition of Saturn's atmosphere from inside Saturn's atmosphere, doing science until the signal could no longer survive the heat. September 15th, 2017. The signal lasted until 11:55 and 46 seconds, Coordinated Universal Time. Then nothing. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. The Cassini-Huygens spacecraft was one of the largest and most complex interplanetary probes ever built. Conceived in the 1980s, designed through the 1990s, and launched on October 15, 1997, it carried 12 scientific instruments and one atmospheric probe, weighed 5,600 kilograms at launch, and was designed to survive the radiation environment of Saturn and operate for decades on nuclear power alone. It traveled 3.5 billion kilometers over 7 years before it reached its destination, and then it orbited Saturn for 13 years, producing more than 450,000 images and contributing to over 4,000 scientific publications. On September 15, 2017, the mission ended deliberately, not by accident, not by failure, but by design. Tonight, you are making that journey from the beginning. You are standing on a launch pad in Florida. It is October 15th, 1997. The air is warm and still carries salt from the Atlantic, 16 kilometers east. Around you, in every direction, the flat coastal scrubland of Cape Canaveral stretches out under a pre-dawn sky. The stars are still visible. In a few minutes, they will be obscured by something much brighter. The rocket behind you is a Titan 4B, one of the largest unmanned launch vehicles ever used by the United States Air Force. It stands 55 meters tall and produces approximately 15,000 kilowatts of thrust at liftoff. Strapped to its upper stage is a spacecraft that took 2 decades to design and build, a collaboration between NASA, the European Space Agency, and the Italian Space Agency, involving engineers and scientists from 17 countries. The spacecraft is called Cassini. It is named for Giovanni Domenico Cassini, the 17th century astronomer who discovered the gap in Saturn's rings that still bears his name, the Cassini division, a 800-kilometer gap between the A and B rings, visible through even a modest telescope. The probe attached to Cassini's side is called Huygens, named for Christian Huygens, the Dutch astronomer who in 1655 discovered Titan, Saturn's largest moon. You are not yet aware of all this history. What you are aware of is the vibration building beneath your feet, a low-frequency resonance, more felt than heard, traveling up through the concrete and into your spine. The countdown reaches 0 at 4:43 in the morning, Eastern Time. The solid rocket boosters ignite. The sound arrives about a second later, not a roar but a physical pressure, a force that pushes against your chest and rattles the fillings in your teeth. The rocket lifts. It moves at first almost impossibly slowly for something that size, a tower of light ascending against gravity, trailing a column of fire and steam that reflects orange across the water of the retention ponds nearby. Within seconds, it has cleared the launch structure. Within 30 seconds, it is tilting eastward over the Atlantic, following the curve of the planet, beginning the burn that will carry it to orbit and beyond. You watch it climb until the light is a point, then nothing. Cassini is gone. It has left Earth, but it will not go directly to Saturn. This is the part that surprises most people who have not studied orbital mechanics. Saturn is so far from the Sun, nearly 10 times farther than Earth, that launching directly to it, even from a rocket this powerful, would have required carrying an impractical amount of fuel. Instead, Cassini's engineers designed a trajectory called a Venus-Earth-Earth Gravity Assist, or VVEJGA, a looping path through the inner solar system that uses the gravitational pull of other planets to accelerate the spacecraft without burning additional propellant. The physics are elegant. When a spacecraft flies past a planet, it enters the planet's gravitational field and is pulled toward it. If the spacecraft's trajectory is calculated correctly, it passes behind the planet relative to its orbital motion and is flung forward, gaining velocity that it keeps permanently. The planet loses an infinitesimally small amount of momentum in the exchange. Newton's laws are satisfied. The spacecraft accelerates for free. Cassini will do this 4 times. First, it flies to Venus, passing within 284 kilometers of its surface on April 26, 1998. The thick Venusian atmosphere glows below, reflecting sunlight with a brightness that would be blinding to human eyes. The planet's gravity pulls Cassini in, whips it around, and throws it back outward with a velocity increase of 7 kilometers per second. It does this again at Venus on June 24, 1999, passing even closer at 600 kilometers altitude, gaining another velocity boost. Then, on August 18, 1999, it comes back to Earth. This is the moment that made some people nervous. Cassini carried 32.8 kilograms of plutonium, 238 dioxide, in its radioisotope thermoelectric generators, the only power source capable of providing electricity at Saturn's distance from the Sun, where solar panels would need to be the size of a tennis court to generate enough energy. The spacecraft passed within 1,171 kilometers of Earth's surface during the flyby, close enough that a navigation error of any significance could have brought it into the atmosphere. It did not. The trajectory was calculated to a precision measured in kilometers across a journey of billions. Cassini swept past Earth at 19 kilometers per second, gained another velocity boost, and continued outward, this time genuinely departing the inner solar system. You are on the spacecraft now. You have been on it since liftoff. You are distributed across its instruments, the cameras, the spectrometers, the magnetometer, the plasma wave antenna, dormant systems in standby mode, conserving power and waiting for the work to begin. The spacecraft rotates slowly to balance thermal loads. Every 24 hours or so, a brief communication session with Earth is maintained. Engineers on the ground confirm your systems are nominal. You respond with telemetry data. Then the signal closes and silence returns. The silence of deep space is not what most people imagine. There is no absolute quiet in a functioning spacecraft. The RTG, the radioisotope thermoelectric generator, produces a constant low-level hum of electrical activity. Attitude control thrusters fire in tiny bursts to maintain orientation. The thermal blankets creak imperceptibly as temperature gradients shift on different faces of the spacecraft. But there are no external sounds. Space is a vacuum. Nothing travels to your exterior sensors but electromagnetic radiation. The sun is shrinking. On the day of launch, the sun subtended an angular diameter of approximately 0.5 degrees in Earth's sky. As Cassini moves outward through the inner solar system, this angle decreases. By the time you pass the orbit of Jupiter on December 30th, 2000, at a distance of 9.7 million kilometers from the giant planet, the Sun is already noticeably smaller and dimmer than it appears from Earth. Jupiter itself fills a significant portion of your visual field. Its cloud bands are clearly resolved. The Great Red Spot, a storm system larger than Earth that has persisted for at least 350 years, is visible as a reddish oval in the southern hemisphere. You spend 6 months near Jupiter. This too is a gravity assist. Cassini gains 2 kilometers per second from the encounter and simultaneously conducts science, imaging Jupiter's atmosphere in collaboration with the Galileo spacecraft, which has been in orbit around Jupiter since 1995. It is the first time 2 operational spacecraft have studied Jupiter simultaneously. You observe features in Jupiter's cloud layers that were not previously resolved: ammonia plume structures rising from the deep atmosphere, lightning in the night hemisphere, auroral curtains at the poles. Then Jupiter falls behind. The outer solar system opens ahead of you. There is very little out here. The density of matter, gas, dust, solar wind particles drops with every astronomical unit of distance from the Sun. Between the orbit of Jupiter and the orbit of Saturn lies a span of 4.3 astronomical units, 643 million kilometers of almost nothing. You travel through it for 2.5 years. During this transit, you are not idle. The instruments are periodically activated for calibration. The cameras are tested. In October 2003, Cassini's radio signals are used in an experiment to test general relativity, a prediction by Albert Einstein that mass causes space-time to curve, and that light passing close to a massive object will be slightly delayed compared to light traveling through flat space. The Sun is used as the massive object. Cassini's radio signal, passing close to the solar limb, arrives at Earth slightly later than it would if space were flat. The measured delay matches Einstein's prediction to within 0.002%. General relativity passes another test, 700 million kilometers from Earth. You continue. The Sun is now roughly 1% as bright as it appears from Earth's surface. It would appear to an unprotected human eye not as a disk, but as an extremely bright star, still the brightest object in the sky by a large margin, but clearly diminished. The temperatures on Cassini's dark faces drop to below -150 degrees Celsius. The RTGs maintain electrical power. The heaters maintain minimum operational temperatures for critical components. And then in early 2004, something appears in the cameras. At first it is a point of light, indistinguishable from a star. Then it resolves, slightly, incrementally, into a shape, a disk. A disk with wings? The rings. They are visible before the planet itself is fully resolved. Saturn's ring system, spanning from 66,900 kilometers above the cloud tops to 483,000 kilometers, a flat disk of ice and rock particles ranging in size from dust grains to boulders, reflects sunlight with extraordinary efficiency. The rings are brighter than the planet. You see them first, and then the planet itself comes into focus. It is enormous. Saturn's equatorial diameter is 120,536 kilometers. Its polar diameter is 108,728 kilometers. It is visibly flattened at the poles due to its rapid rotation, completing one rotation in approximately 10.7 hours. Despite its size, its upper atmosphere is a banded structure of pale gold, cream, and faint brown, ammonia ice crystals forming the uppermost cloud deck, with ammonium hydrosulfide clouds beneath, and water ice clouds deeper still. You have been traveling for 6 years, 7 months, and 16 days. You are almost there. The approach continues for months. Cassini is performing continuous observations, imaging Saturn's moons, studying the ring structure from a distance, calibrating instruments against known targets. Among the moons, one draws immediate attention: Titan. It is the only moon in the solar system with a substantial atmosphere, a nitrogen-methane envelope 1.5 times denser at the surface than Earth's atmosphere at sea level. From a distance, Titan looks like an orange sphere, its surface completely hidden beneath a permanent photochemical haze produced when methane molecules are broken apart by solar ultraviolet radiation and recombine into complex organic compounds called tholins. No spacecraft has ever seen Titan's surface. Cassini will change that. But before any of that can happen, there is one critical moment that everything depends on, a moment that has been planned, calculated, and rehearsed for years, a moment that will occur on June 30th, 2004, when Cassini has been in space for 6 years, 8 months, and 15 days. Saturn orbit insertion. You carry enough propellant for one chance to slow down enough to enter orbit. If the main engine fails to fire, or fires incorrectly, or fires for the wrong duration, Cassini will pass Saturn and continue into interplanetary space, never to return. The entire mission, the careers of hundreds of scientists, 2 decades of engineering work, will be over. The engine must fire. It must fire for exactly 96 minutes and 19 seconds. It must reduce Cassini's velocity by exactly 622 meters per second, enough to drop from a hyperbolic flyby trajectory into a closed elliptical orbit around Saturn. There is no room for error. On June 30th, 2004, at 1:12 UTC, the main engine ignites. You feel, or rather you register through your accelerometers, the thrust beginning, 445 newtons of force, applied continuously, decelerating you against your direction of travel. The fuel, monomethylhydrazine and nitrogen tetroxide, a hypergolic propellant combination that ignites on contact, burns at a controlled rate. 50 minutes into the burn, you pass through the ring plane for the first time. The rings, which from a distance looked like thin, flat discs, are revealed close up to be something far more complex. You are passing through a gap between the F ring and the outer edge of the A ring. The particle density here is relatively low, but not zero. Small grains of ice, some no larger than smoke particles, some the size of a marble, stream past your exterior. The high-gain antenna has been oriented forward as a shield. You can hear, through the vibration sensors, the impact of particles on the antenna dish, not a roar. A soft, irregular patter, like rain on a metal roof. You emerge from the ring plane. The engine continues to burn. At 2:48 UTC, 96 minutes and 19 seconds after ignition, the engine shuts down. The accelerometers confirm, nominal, the velocity reduction is within specification. The trajectory calculation software confirms, Cassini is in orbit. It is in orbit around Saturn. After 6.5 years, after 35 billion kilometers of interplanetary travel, after 4 gravity assists and 1 close pass of Earth, after sleeping through the transit from Jupiter to Saturn and awakening as the planet grew in the cameras, you are here. You are staying. The first orbit is a large looping ellipse, a capture orbit designed to carry you far above the ring plane and back, giving the instruments a chance to observe Saturn from multiple geometries before the mission begins in earnest. As you swing out along the capture orbit, you look back. Saturn fills a significant fraction of your visual field. The rings extend outward from the equator in both directions, tilted at 27 degrees to your current viewing angle, catching the sunlight and casting a curved shadow across the planet's upper northern hemisphere. The bands of the atmosphere are clearly resolved. Near the terminator, the boundary between day and night, you can see the ring shadow in sharp relief against the pale ammonia clouds. You have looked at photographs of this. Every person on Earth who owns a small telescope has looked at this, but you are looking at it from 20,000 kilometers away, in real time, with 12 scientific instruments running, and no photograph was ever taken from exactly here. No machine ever came this close before. The Huygens probe, strapped to your side since 1997, is still dormant. It has its own power source, a set of lithium batteries charged by the RTG over the years of transit, and its own instruments, an atmospheric structure instrument, a gas chromatograph and mass spectrometer, a Doppler wind experiment, a surface science package, and cameras. It weighs 319 kilograms. It is a parachute-equipped entry vehicle designed to survive the descent through Titan's atmosphere. It will not be deployed for 6 more months. For now, you orbit. The first close Titan flyby, Ta, in the mission's internal numbering, occurs on October 26, 2004, at an altitude of 1,200 kilometers. The radar instrument sweeps swaths of Titan's surface through the opaque haze, bouncing radio waves off the hidden terrain and receiving the echoes. The VIMS instrument, the Visual and Infrared Mapping Spectrometer, probes through atmospheric windows at specific near-infrared wavelengths, where the haze is less absorbing, catching hints of surface features below. What you see, or rather what the instruments begin to construct, are structures that look like drainage channels, like riverbeds. On a moon with a surface temperature of -179 degrees Celsius, there are features that look like they were carved by flowing liquid, not water. Water is frozen solid at these temperatures, but methane. Liquid methane. The hypothesis that Titan might have a liquid methane cycle, analogous to Earth's water cycle with evaporation, cloud formation, rainfall, and surface drainage, gains immediate support from these first radar swaths. But Titan's surface will not be fully understood from orbit. It requires direct measurement. On December 25, 2004, exactly 1 year, 2 months, and 10 days after your engine fired to enter orbit, Huygens separates from Cassini. A set of pyrotechnic bolts fires, cutting the mechanical and electrical connections between the two spacecraft. A set of 3 spring mechanisms pushes Huygens away at 0.35 meters per second. The two spacecraft drift apart. You, Cassini, perform a deflection maneuver to ensure you will not follow Huygens into Titan's atmosphere. You must remain in orbit to serve as a relay station, receiving Huygens transmissions and forwarding them to Earth. For 21 days, Huygens coasts on a ballistic trajectory toward Titan. On January 14, 2005, at 9:06 UTC, Huygens enters Titan's atmosphere at 6.1 kilometers per second. The heat shield, made of aerogel tiles backed by carbon phenolic material, begins to glow as it decelerates against the dense nitrogen-methane atmosphere. Peak deceleration reaches 16 G. The exterior temperature of the heat shield rises above 1,900 degrees Celsius. For 2 minutes and 20 seconds, the heat shield absorbs the energy of entry. Then, at 160 kilometers altitude, the main parachute deploys. The descent slows to approximately 20 meters per second. Huygens begins transmitting on 2 frequencies. Channels A and B, and U Cassini receive the signal from 60,000 kilometers overhead. The first human-made object is descending through an atmosphere that no instrument has ever directly measured. The descent takes 2 hours and 27 minutes. The gas chromatograph mass spectrometer samples the atmosphere at multiple altitudes, confirming nitrogen 98.4%, methane approximately 1.4% below the tropopause, higher in the stratosphere, argon 40 in trace amounts. Complex organic molecules, nitriles, hydrocarbons, suspended in the haze layers. The imaging system captures frames through the orange murk as Huygens descends. The surface, when it finally appears at low altitude, is not what anyone expected exactly, but also not entirely surprising. A flat plain covered with rounded pebbles, water ice pebbles, rounded by some ancient liquid flow, and darker, finer material between them. Drainage channels are visible extending from brighter elevated terrain to the south toward the darker flat plain. At 11:38 UTC, Huygens touches down. Surface temperature minus 179.5 degrees Celsius. Surface pressure 1.47 bars, 1.47 times Earth's sea level atmospheric pressure. The surface is soft, slightly yielding, the consistency of wet sand or a creme brulee, the probe's engineering team will later report. For 72 minutes, Huygens transmits from the surface. Then its batteries are exhausted. The signal stops. U Cassini are still overhead, still receiving for as long as Huygens transmits, still relaying back to the 3 receiving stations on Earth, Parkes in Australia, the Green Bank Telescope in West Virginia, the Very Large Array in New Mexico, that are listening for the carrier signal of a 348-kilogram machine sitting on the surface of a world 1.2 billion kilometers away. When the signal stops, you are already continuing, already on the next orbit, already pointing instruments at the next target, because there is so much left to do. The moons of Saturn number, at the time of Cassini's arrival, 62 known bodies, a number that will grow to 83 with subsequent observations. Most are small, irregular, geologically dead, captured asteroids or objects that coalesced in the early solar system and have not changed significantly since, but not all of them. There is one that will become the most discussed discovery of the entire mission. It is a small moon, only 504 kilometers in diameter, smaller than the state of Arizona, and it orbits Saturn at a distance of 238,042 kilometers, completing one orbit every 32.9 hours. It is tidally locked to Saturn, meaning it always shows the same face to the planet, just as Earth's moon always shows the same face to Earth. Its surface, based on early observations, is extremely bright, brighter than almost any other body in the solar system, reflecting nearly 100% of incoming sunlight. This high albedo, combined with early observations suggesting surface activity, brings it to immediate scientific attention. It is called Enceladus, and in February 2005, you fly past it for the first time. What the magnetometer detects, an unexpected distortion in Saturn's magnetic field near the south polar region of Enceladus, begins a chain of investigation that will ultimately overturn assumptions about where life might exist in the solar system. But that discovery is still forming, still gathering evidence, still waiting for the close flyby that will confirm what the instruments are beginning to suspect. For now, you orbit on. Saturn's rings fill the cameras. You spend weeks imaging specific ring features, waves and spirals generated by gravitational resonances with Saturn's moons, sharp-edged gaps where small embedded moonlets clear paths through the ring material, bright clumps and streamers in the F-ring that change shape from orbit to orbit. The B-ring, the densest and brightest, contains structures that still resist full theoretical explanation: self-gravity wakes, azimuthal brightness asymmetries, unexplained opacity variations on scales of kilometers. The more you look, the more complex it becomes. A passing glance at Saturn from Earth's surface suggests a simple system, a planet with rings. The closer you get, the more apparent it becomes that the rings are a dynamic, continuously evolving structure, billions of years old and still changing. Your orbit is not fixed. It is designed to evolve. Over the 4-year primary mission, orbital mechanics calculated by the navigation team at JPL will gradually reshape your path around Saturn. Some orbits will carry you out to the edge of the system, beyond the orbit of Titan, nearly 1 million kilometers from Saturn. Others will bring you close in, grazing the outer edge of the rings. Some will take you over Saturn's poles, where you can look straight down at the hexagonal cloud feature that persists in the North Polar region, a standing wave in the atmosphere maintained by Saturn's rotation, 6 sides each, nearly 14,500 kilometers long, with wind speeds at the edges reaching 320 kilometers per hour. Some will give you close approaches to the major moons: Titan, Enceladus, Dione, Rhea, Tethys, Mimas, each with its own surface geology, its own orbital history, its own unanswered questions. You have 13 years. You are going to need them. The primary mission runs from July 2004 to June 2008. At its conclusion, Cassini has completed 74 orbits of Saturn, performed 44 Titan flybys, and 3 Enceladus flybys, including one that begins to clarify what the magnetic field anomaly near the South Pole means. NASA approves an extension, the Cassini Equinox mission, running from 2008 to 2010, covering Saturn's equinox, the moment when the Sun crosses Saturn's equatorial plane, and the rings seen edge on from the Sun cast no shadow on the planet. Then another extension, the Cassini Solstice mission, running from 2010 to 2017, covering Saturn's northern summer solstice and the full seasonal cycle. The original mission, designed for 4 years, will run for 13. And throughout all of it, you are learning. The South Polar region of Enceladus, the lakes of Titan, the ring structures. The storms that occasionally erupt in Saturn's atmosphere, massive convective systems that can encircle the entire planet. The interaction between Saturn's magnetosphere and its rings and moons, the composition of the rings, the origin of the rings. Every orbit adds data. Every flyby adds specificity. Every year, the picture of the Saturnian system becomes more detailed, more nuanced, more surprising. And slowly, over years, the fuel that Cassini carries for its thrusters, the hydrazine that fires the attitude control jets, and the maneuver engines, is being used up, not quickly, carefully, slowly conserved by the mission planners. But the supply is finite. A spacecraft with no propellant has no ability to maneuver. Without maneuvering, it cannot maintain its orbit, cannot keep its solar occultation geometry, cannot point its instruments. Without pointing, it cannot do science. And an uncontrolled spacecraft in the Saturnian system poses a contamination risk. If it were to impact Enceladus or Titan by chance, even the dormant biological material that hitches rides on spacecraft surfaces could complicate future searches for indigenous life. The decision that will eventually end Cassini begins not with dramatic discussion, but with a quiet reckoning. The fuel will eventually run out. The question is not whether, but when, and what to do about it. The answer, reached through years of discussion among mission planners, astrobiologists, and planetary protection officers, is to end the mission deliberately in a way that is both scientifically valuable and environmentally responsible. The spacecraft will be sent into Saturn, but not yet. You still have years to go, years of orbits, years of Titan flybys, years of Enceladus approaches, each one refining the measurements of the plume, years of ring observations that will contribute to more publications than any previous planetary mission, and one more set of orbits that has never been done before, a final daring sequence that will take you somewhere no spacecraft has ever been. Inside the rings, between Saturn's cloud tops and the inner edge of the D ring, the innermost ring, there is a gap approximately 2,000 kilometers wide. It is not empty. It contains ring particles, dust, and charged particles that have not been directly sampled. It has never been traversed by a spacecraft because no spacecraft has ever survived the entry conditions, and because no mission with other objectives could afford the risk. Cassini can afford it now, because there is nothing left to lose. The grand finale will begin in late April 2017, but between now and then, there is still the rest of the mission to complete. There are still moons to fly past, storms to image, ring structures to study, plumes to sample. Tonight, you are not at the end. Tonight, you are still in the middle years, the long, extraordinary middle of a mission that spans more than a decade. The rings are turning outside your cameras. Titan is below, its orange haze catching sunlight. Enceladus is ahead on the next orbit, its south pole already beginning to intrigue the scientists watching your data from the ground. You orbit on. The universe is patient. So are you. The orbit that carries you toward Enceladus takes approximately 33 hours to complete. You know this because your onboard clock is accurate to within microseconds, synchronized against atomic reference standards, updated periodically through the Deep Space Network's constellation of large dish antennas scattered across 3 continents. You know the duration of every orbital arc, every flyby approach, every engine burn, calculated to fractions of a second years in advance by a navigation team at the Jet Propulsion Laboratory in Pasadena, who have modeled the gravitational influences of Saturn, its 62 moons, the Sun, Jupiter, and even the faint pressure of solar radiation pushing against the face of your high-gain antenna. The universe operates on mathematics, and you have learned to trust the mathematics completely. Enceladus grows in the cameras over the course of several hours. It is small, 504 kilometers in diameter, smaller than the state of Arizona, smaller than the distance from New York to Boston, and at first it resolves as a point brighter than the stars around it, then as a disk, then gradually as a world with distinguishable surface features. Even at this distance, before the close approach begins, one thing is immediately apparent. Enceladus is white. Not gray, not the mottled beige of most rocky bodies in the outer solar system, not the reddish-brown of tholins that stains so many icy surfaces. White, a brightness that stands out against the black of space and the pale gold of Saturn's cloud bands in a way that immediately marks it as different. Its geometric albedo, the ratio of reflected light to incoming sunlight, is approximately 1.38. This is higher than 1.0, which would represent a perfect mirror reflection from a flat surface. The value above 1.0 is possible for spherical bodies due to the backscattering properties of fine-grained ice. Particles at the exact opposition geometry scatter light back toward the source more efficiently than a flat surface would. In practical terms, Enceladus reflects more sunlight than falls on it from certain angles. It is the most reflective body in the solar system. This was already known before Cassini arrived. What was not known was why. A surface of pure water ice, exposed to the vacuum of space over billions of years, should slowly darken. Micrometeorite impacts and cosmic ray bombardment create amorphous carbon compounds in ice, a process called space weathering that gradually reddens and darkens icy surfaces across the outer solar system. Almost every icy moon and Kuiper Belt object shows evidence of this darkening over geological timescales. Enceladus does not. Its surface is being continuously renewed. Fresh, clean ice is being deposited at a rate fast enough to keep pace with the darkening, and the only mechanism capable of producing this renewal at the scale required is the plume system. Material ejected from the South Pole, lofted into space, follows ballistic trajectories and eventually settles back onto the surface, creating a continuous gentle snowfall of freshwater ice particles across much of the moon. Enceladus is snowing on itself. You approach the South Pole on the E3 flyby, March 12, 2008, descending from the orbital plane toward the terrain that the magnetometer data and early thermal measurements have already flagged as anomalous. The surface below is approaching at 14.4 kilometers per second relative to your position, 14 kilometers every second, the distance between cities covered in the time it takes to draw a breath. At closest approach, 48 kilometers above the surface, the tiger stripe fractures are not distant geological features. They are immediate. They fill the field of view of every instrument pointed downward. Each fracture, Baghdad sulcus, Cairo sulcus, Damascus sulcus, Alexandria sulcus, is a linear depression approximately 500 meters deep and 2 kilometers wide, running roughly parallel to its neighbors, each approximately 130 kilometers long. Their walls glow in the infrared. The Sears instrument, composite infrared spectrometer, measures temperatures along the fractures, reaching up to 197 Kelvin, compared to the surrounding undisturbed surface ice at approximately 68 Kelvin. 129 degrees warmer than the ice around them. And above the fractures, rising into the near vacuum above the surface, material is moving upward. The VINS instrument, Visual and Infrared Mapping Spectrometer, detects water ice in its crystalline form above the tiger stripes, not amorphous. This distinction matters enormously. Water ice in space normally adopts an amorphous, disordered molecular structure over time, as cosmic radiation disrupts the crystal lattice one atom at a time. Crystalline ice requires temperatures above approximately 110 Kelvin to form and maintain its ordered structure. The presence of crystalline water ice in the plume material confirms that it is freshly formed, coming directly from a warm liquid reservoir below, crystallizing as it erupts and expands into the cold vacuum above the surface. This ice was liquid moments ago. The INMS instrument, Ion and Neutral Mass Spectrometer, is pointed directly into the plume column as you pass through it. The instrument intake faces into the direction of travel, collecting the plume material at 14.4 kilometers per second and directing it into the mass spectrometer chamber, where individual molecules are ionized and sorted by their mass-to-charge ratio. The spectrum that returns shows, in order of abundance, water vapor, H2O dominant, comprising more than 90% of plume material by number density, carbon dioxide, CO2 approximately 3.5%, methane, CH force approximately 1.6%, ammonia, NH3 approximately 0.8%, molecular hydrogen, H2, trace amounts, but clearly and unambiguously present, and a collection of heavier organic molecules, masses consistent with propane, acetylene, formaldehyde, and other carbon-bearing compounds in the mass range of 28 to 100 atomic mass units. Each of these compounds carries information about what is happening below the surface. The water is the baseline. There is a liquid water reservoir below, and it is vaporizing at the fractures, where the pressure differential between the subsurface and the surface vacuum drives the fluid upward. The ammonia modifies the water chemistry. Ammonia dissolves in water to form ammonium hydroxide, which acts as an antifreeze, lowering the freezing point of the ocean and allowing it to remain liquid at temperatures slightly below 273 Kelvin. The molecular hydrogen is the finding that will take years to fully interpret, and when it is interpreted, it will change how scientists think about the habitability of the outer solar system. On Earth, hydrogen gas dissolved in hydrothermal vent water is produced primarily when hot water, heated by contact with the deep crust, reacts chemically with iron and magnesium-rich minerals called olivine and pyroxene. These minerals contain iron in the Fe+ oxidation state. When superheated water contacts them, the iron oxidizes from Fe+ to Fe+, stripping hydrogen atoms from water molecules and releasing them as H2 gas. This process, called serpentinization, is one of the most geochemically significant reactions in Earth's ocean floor, operating continuously wherever hot water circulates through appropriate rock. The organisms that live around hydrothermal vents on Earth harvest the energy stored in this hydrogen. Methanogens, among the most ancient lineages of life on Earth, combine hydrogen with carbon dioxide through a metabolic process called hydrogenotrophic methanogenesis, producing methane and water. These organisms require no sunlight. They require no photosynthesis. They operate in total darkness, kilometers below the surface, as long as the Serpentisci reaction continues to produce hydrogen and as long as carbon dioxide is available. Both are present in the plume of Enceladus. The same chemistry that feeds life in Earth's darkest ocean is operating inside a moon of Saturn. The flyby sequence continues across the extended missions. E5 in October 2008 passes at 25 kilometers, the closest approach yet, barely the altitude of a high-flying aircraft above Earth, but above a world with 1.1% of Earth's surface gravity and a surface covered in ice that was liquid perhaps hours before. E6 in November 2008. E7 in November 2009. Each encounter refines the compositional and structural picture of the plume. The UVS instrument, ultraviolet imaging spectrograph, maps the three-dimensional geometry of the plume system in ultraviolet light during multiple flybys, resolving not a single diffuse jet, but a complex arrangement of at least 101 discrete individual sources along the tiger stripe fractures. Most of these sources are concentrated along Damascus-Sucus and Baghdad-Sucus. Each source is a discrete vent, a point where subsurface fluid reaches the surface at sufficient temperature and pressure to flash to vapor and accelerate upward. The total mass flux from all sources combined is approximately 200 kilograms per second. 200 kilograms of water vapor and ice particles erupting from the surface of Enceladus every second, continuously without interruption, 24 hours a day, for a timescale that the thermal budget of the interior suggests may span hundreds of millions of years. Enceladus's surface gravity is only 0.113 meters per second squared, about 1.1% of Earth's surface gravity. Escape velocity from the surface is approximately 239 meters per second. The plume erupts at velocities ranging from 300 to more than 2,000 meters per second, depending on the vent. Most of this material is moving faster than escape velocity. It leaves Enceladus behind. It spreads outward into the space around Saturn, some settling back onto the surface as the continuous snowfall that keeps the moon bright, some being ionized by solar radiation and captured into Saturn's magnetosphere as a plasma torus near Enceladus's orbit, and some, the finest sub-micrometer ice particles, drifting gradually along the orbital path and accumulating in a diffuse ring between approximately 180,000 and 480,000 kilometers from Saturn's center. This is the E-ring. Everything in it came from the south pole of a moon 504 kilometers wide. The E-ring is Enceladus made visible, its interior made external, its ocean made photons, its chemistry spread across a ring system that extends for hundreds of thousands of kilometers. The gravity science investigation, conducted by precisely tracking the Doppler shift of Cassini's radio signal during close Enceladus flybys, measuring tiny variations in spacecraft velocity caused by gravitational tugs from Enceladus's internal mass distribution, produces results published in 2014 that confirm what the other instruments had long implied. The south polar region of Enceladus has a mass deficit. The material that should be there, solid rock and ice distributed uniformly, is not there. Something less dense than solid rock is occupying that space. The data constrains the subsurface body to a regional liquid water ocean beneath the South Polar terrain, at least 10 kilometers deep, capped by an ice shell 30 to 40 kilometers thick. A later analysis combining gravity measurements with precise measurements of Enceladus's physical libration, the way the moon wobbles slightly in its orbit because its ice shell is decoupled from its rocky interior, extends this estimate to a global ocean, a continuous body of liquid water surrounding the entire rocky core beneath a global ice shell, an ocean that covers an entire world. Held liquid by the gravitational kneading of Saturn, the tidal flexing imposed by the two, one orbital resonance between Enceladus and Dione, which continuously deforms the moon's interior as it moves through the varying gravitational field along its orbit, generating an estimated 15 to 25 gigawatts of frictional heat. The final major Enceladus flyby, E21, October 28, 2015, passes at 49 kilometers altitude through the densest part of the plume at 8.5 kilometers per second. The INMS is configured for maximum sensitivity. The data from this encounter contains the detection that will be the most scientifically significant finding of the entire Enceladus investigation. Silica nanoparticles. Silicon dioxide particles, 2 to 9 nanometers in diameter, smaller than a virus, smaller than the wavelength of visible light, detected in the plume material, and consistent with formation at temperatures above 90 degrees Celsius in alkaline conditions, pH between 8.5 and 10.5. On Earth, particles of this exact type, size, and chemistry form in one known environment, where superheated hydrothermal vent fluid at temperatures above 90 degrees Celsius mixes rapidly with cooler seawater. The rapid temperature drop causes silica to precipitate from solution as nanoparticles, which are then carried upward by the hydrothermal plume into the water column. To form these particles on Enceladus, water must be reaching temperatures above 90 degrees somewhere in the interior, and then mixing rapidly with cooler water. The only place that can happen is at the seafloor. There are hydrothermal vents at the bottom of Enceladus's ocean. Not inferred from models, not extrapolated from theory, measured through the physical and chemical fingerprints of particles that formed at the seafloor of an alien ocean, rose through kilometers of water, erupted through fractures in the ice, and were collected by an instrument on a spacecraft passing 49 kilometers overhead. You complete E21 and arc back onto your orbital path. Below you, through 40 kilometers of ice and 10 or more kilometers of liquid water, chemistry is happening at the floor of an ocean that has existed for hundreds of millions of years. Whether that chemistry supports life, whether methanogens or their equivalent are harvesting the hydrogen produced by serpentinization in the dark interior of this small moon, is a question Cassini cannot answer. But it is no longer a hypothetical question. It has a location, it has measured conditions, it has chemical evidence of the process that feeds life in Earth's deepest oceans. It is real enough to design a mission for. You orbit on through the middle years. There are 62 known moons of Saturn at the time of Cassini's arrival, a number that will grow to 83 by the time ground-based astronomers finish cataloging the smaller, dimmer bodies revealed by improved survey techniques. Most of them are small, irregularly shaped, geologically inert, captured objects from the early solar system or fragments of larger bodies broken apart by collisions, now orbiting Saturn in stable paths without significant geological activity. But several of them are not. Dione, 1,123 kilometers in diameter, shows wispy bright streaks across its trailing hemisphere, features resolved by Cassini's cameras as networks of ice cliffs, the walls of tectonic fractures where the surface has pulled apart and fresh interior ice has been exposed. The fractures run for hundreds of kilometers. They are older than Enceladus's tiger stripes, geologically quieter, no longer actively erupting, but evidence that Dione too experienced a period of internal heating and tectonic activity at some point in its history. Rhea, 1,528 kilometers across, is the second largest moon of Saturn, and like Dione, it carries a fractured surface. But Rhea holds a particular intrigue. In 2008, the MIMI instrument detected a depletion of energetic electrons in Saturn's magnetosphere near Rhea's orbit, a pattern consistent with absorption by a ring of debris in orbit around Rhea itself. If confirmed, it would make Rhea the first moon known to possess its own ring system. Subsequent imaging attempts failed to resolve any visible ring structure, and the interpretation remains debated. But the electron depletion is real, and its cause has not been definitively resolved. Iapetus carries one of the most striking features in the solar system, a two-tone coloration so extreme that Giovanni Cassini, the astronomer for whom the spacecraft is named, noticed it through a 17th century telescope and deduced that one hemisphere must be very dark and the other very bright. Cassini, the spacecraft, resolves this in detail during a September 2007 flyby at 1,227 kilometers altitude. The leading hemisphere is covered in dark material, reddish-brown, almost black in places, with albedo as low as 0.03, while the trailing hemisphere is bright water ice, with albedo close to 0.6. The boundary between them is sharp at some latitudes, gradual at others. The dark material is not indigenous to Iapetus. It is debris swept up from the outer moons, primarily Phoebe, an irregular captured object orbiting retrograde far outside the main moon system, which is continuously shedding dark dust as micrometeorites impact its surface. This dust drifts inward through the Saturnian system on slowly decaying orbits, preferentially coating the leading hemisphere of Iapetus as the moon moves through it. The dark material absorbs sunlight, warming the leading hemisphere and driving a thermal migration of water ice from warm regions to the permanently cold polar areas, further concentrating the dark material in the equatorial band. The pattern you see on Iapetus is the accumulated record of billions of years of orbital dynamics. One moon darkened by the dust of another moon far away. Mimas, 396 kilometers in diameter, the smallest body in the solar system massive enough that its own gravity has pulled it into a roughly spherical shape, carries the Herschel crater, a 139-kilometer impact basin so large relative to the size of the moon that the impact which created it must have come close to shattering Mimas entirely. The central peak of Herschel rises 6 kilometers from the crater floor. The walls are 5 kilometers tall. When Cassini images Mimas in full sunlight with Herschel visible, the resemblance to a fictional space station from popular culture is noted by virtually everyone who sees it. Mimas is also cold. Strangely, unevenly cold in a pattern that does not match its crater distribution or its distance from Saturn. The Sears instrument maps thermal emission from Mimas's surface and finds a Pac-Man-shaped warm region, a pattern consistent with areas where the regolith has been compacted by past meteor bombardment, changing how it absorbs and releases heat through the day. The same instrument finds evidence for a possible subsurface ocean inside Mimas, announced in research published years after the mission ends, based on a subtle libration in Mimas's rotation that suggests the ice shell may be decoupled from a liquid interior. Another ocean inside another moon. The Saturnian system, the more you study it, is not a collection of geological relics. It is a collection of active, evolving worlds. Between 2010 and 2016, the Cassini solstice mission carries the observation campaign through Saturn's full northern spring and into early northern summer. The scientific scope of the mission has by this point expanded far beyond anything the original design document specified. A catalog of measurements, magnetometer readings, spectral data, imaging mosaics, radio science results, dust impact records, fills data archives that will take generations of scientists to fully analyze. In December 2010, Saturn erupts. The first signs appear on December 5th, a bright white cloud feature in the northern hemisphere, visible in Cassini's cameras as a compact convective plume pushing through the upper cloud deck. Within a week, it has spread longitudinally by thousands of kilometers. Within a month, it has encircled the planet, a band of disturbed, turbulent cloud stretching across latitudes between 30 and 50 degrees north, completely girdling Saturn in a storm system larger than the entire surface area of Earth. This is a great white spot, a large-scale convective storm that erupts on Saturn approximately once per Saturnian year, roughly every 29 to 30 Earth years, when convective instability in the deep troposphere finally overcomes the stable atmospheric stratification and breaks through to the upper atmosphere in a catastrophic release of latent heat. Cassini is the first spacecraft in orbit at Saturn when one occurs. The Sears instrument maps the thermal structure of the storm's anvil, the broad mushroom-shaped cloud top where convective columns detrain into the stable upper atmosphere. At the anvil top, temperatures are 225 Kelvin as expected for the tropopause region, but within the stratospheric beacon, the warm anomaly that develops above intense convective systems, temperatures reach 220 Kelvin at pressure levels where models predict 160 Kelvin. The storm is heating Saturn's stratosphere 60 degrees above its expected background temperature. For comparison, the most intense tropical cyclones on Earth produce stratospheric temperature anomalies of perhaps 5 to 10 degrees. This storm is producing an anomaly 12 times that magnitude in Saturn's much colder, more stable stratosphere. The lightning within the storm, measured by the radio and plasma wave instrument, fires at rates exceeding several hundred discharges per second at peak intensity. Individual lightning channels persist for up to 8 seconds. The radio frequency emission they produce, Saturn electrostatic discharge, or SAD, is detectable by instruments on Cassini from tens of thousands of kilometers away, a continuous crackling of static that fills the radio channels for the 265 days the storm persists, before finally dissipating in mid-2011. You watch it build, peak, and decay from orbit. You watch Titan's seasons turn. Saturn's year, the time to complete one orbit of the Sun, is 29.4 Earth years. A single Saturnian season therefore lasts more than 7 Earth years. Over the course of Cassini's mission, Saturn moves from southern summer through equinox in August 2009 and into northern spring and then northern summer. Titan orbiting Saturn and pointing the same hemisphere towards Saturn always experiences these seasons as changes in solar illumination angle, atmospheric circulation patterns, and the methane-ethane weather that cycles between its polar lakes and its equatorial dune fields. By 2015, the radar instrument has mapped approximately 67% of Titan's surface. The polar regions are dominated by liquid bodies. The northern polar region, now in spring, receiving increasing sunlight after years of winter darkness, contains the largest, Ligeia Mare at approximately 126,000 square kilometers, Punga Mare at 61,000 square kilometers, and Kraken Mare at approximately 400,000 square kilometers, larger than Earth's Caspian Sea and Lake Superior combined. Kraken Mare is deep. During a radar altimeter pass crossing the northern basin of Kraken Mare, the instrument failed to detect a bottom reflection at depths exceeding 160 meters, the maximum measurable depth given the instrument's sensitivity parameters. The actual depth may be considerably greater. The surface of Kraken Mare is flat to within the measurement precision of the instrument, consistent with a calm liquid surface, unperturbed by significant wave activity at the time of measurement. The composition of Ligeia Mare has been directly measured by the VIMS instrument, observing solar specular reflection, sunglint, off the lake surface. The ratio of methane to ethane is approximately 4.5 to 1, with ethane enriched relative to what pure atmospheric condensation would predict. This enrichment is consistent with a long history of preferential methane evaporation, leaving ethane behind, concentrated by years of the methane-ethane weather cycle. These lakes are aging. Their chemistry carries the record of seasons that span decades. The equatorial dune fields are equally vast. The Bellet dune field alone covers approximately 2.5 million square kilometers, larger than the Indian subcontinent. The dunes are composed of organic material, tholins, the complex reddish-brown polymer compounds formed when ultraviolet radiation breaks apart methane and nitrogen molecules in the upper atmosphere, and the resulting fragments recombine into polycyclic aromatic hydrocarbons, nitriles, and other large organic molecules that gradually rain out of the atmosphere and accumulate on the surface. The total estimated mass of organic material on Titan's surface, in the lakes and the dunes suspended in the haze, is on the order of 10 1/2 kilograms. This quantity of carbon-bearing molecular complexity has been accumulating, driven by solar ultraviolet energy acting on a simple atmosphere of nitrogen and methane for the full age of the solar system, 4.5 billion years. Titan is not a living world, at least not in any way the instruments can detect. But it is a world where the ingredients for biology have been accumulating for longer than Earth has had complex life, where every component of the prebiotic chemistry that preceded life on Earth, organic molecules, liquid solvent, energy gradients, is present even if the solvent is methane rather than water, and the energy gradient is tidal rather than solar. In the Selk impact crater, a relatively young impact feature approximately 80 kilometers in diameter, near Titan's equatorial region, the energy of the impact event may have temporarily melted the water ice bedrock, creating a transient pool of liquid water mixed with the organic tholins present on the surface for perhaps hundreds to thousands of years after the impact, before the liquid water refroze in Titan's -179-degree environment. This water-organic mixture would have undergone chemistry similar to what laboratory experiments suggest occurred in Earth's early prebiotic ocean. Then it froze. And whatever chemistry happened during those centuries, whatever molecules formed and reacted and recombined in that brief window of liquid water, is now preserved in the frozen crater floor, a chemical record of a temporary warm period, archived in ice at a specific location on Titan's surface. The Dragonfly rotorcraft mission, approved by NASA in 2019, targeting arrival at Titan in the 2030s, is designed to land in the equatorial dune fields, characterize the baseline organic chemistry of the surface, and eventually fly to the cell crater to directly sample this preserved prebiotic chemistry. It will fly using Titan's thick atmosphere for lift, 4 pairs of rotors generating sufficient thrust in an atmosphere 1.5 times denser than Earth's under gravity, only 1/7 of Earth's. It will cover approximately 175 total kilometers over multiple flights, each landing site a new laboratory. Cassini found the location. Dragonfly will go there. But all of that is still years away from this moment. Right now, it is 2016. Saturn's northern hemisphere is moving into summer, and the hexagonal vortex at the North Pole, which in 2012 appeared as a blue-gray haze region within the hexagonal jet stream, has changed color. It is now golden. The photochemical haze within the hexagonal region has shifted composition as sunlight returns after years of polar winter darkness. Ultraviolet radiation is driving new chemical reactions in the upper atmosphere, producing haze particles of different size and composition that scatter incoming sunlight at different wavelengths. A planet's color is changing because of a geometry. A star is rising over a pole, and the atmosphere is responding. Inside the hexagonal region, a compact polar vortex approximately 2,000 kilometers in diameter has intensified as spring progresses, a cyclonic structure with a clear central eye and organized convective cloud bands rotating at approximately 150 meters per second at the cloud top level. This vortex is nested inside the hexagonal jet stream like a storm inside a frame, a circular feature maintained within a 6-sided standing wave, both of them driven by the same deep atmospheric dynamics rooted in Saturn's interior rotation. You image it from multiple orbital geometries over dozens of passes, building a 3-dimensional picture of the flow structure that no single orbit could provide. The fuel budget narrows. The hydrazine reserves that power the attitude control thrusters, not just the main engine, but the small thrusters that maintain pointing, that correct wobbles, that keep the instruments aligned with their targets, are now measured carefully against the remaining mission plan, not depleted, not empty, but finite in a way that has become the primary constraint on everything the mission does. Mission planners have been managing this budget for years, trimming unnecessary maneuvers, choosing the most efficient trajectories between targets, accepting slightly suboptimal geometries in exchange for propellant savings. The result is that the fuel remaining in late 2016 is enough to complete the planned final sequence, but not much more. The grand finale requires all of it. Every remaining kilogram of hydrazine has been allocated. In April 2017, the final Titan flyby will reshape Cassini's orbit in a way that cannot be reversed. The trajectory will dip below the D ring and into the 2,000 kilometer gap between Saturn's innermost ring and its cloud tops. Each subsequent orbit will pass through this gap, measuring, sampling, transmitting, until the propellant is gone and attitude control is lost and the atmosphere takes over. 22 passes through the gap, then Saturn. But before that, before the grand finale begins, there is one final act of the middle mission that matters. On April 22nd, 2017, Cassini makes its 127th and final flyby of Titan, designated T-126. The flyby altitude is 979 kilometers. At that distance, Titan's gravity exerts a specific, calculated gravitational tug on the spacecraft's trajectory, a tug that the navigation team has been planning to use for 3 years. The tug reshapes the orbit precisely, pulling the apoapsis inward, redirecting the next periapsis from a safe distance above the ring system to a point inside the rings, between the D-ring's inner edge and the uppermost layer of Saturn's atmosphere. Titan pushes you in. From the moment T-126 is complete, there is no maneuver available that could return Cassini to a safe orbit. The propellant needed for such a maneuver does not exist. The mathematics of the trajectory, the same mathematics that brought Cassini from Earth to Venus, to Earth to Jupiter to Saturn in 1997, calculated to precisions of kilometers across billions of kilometers of travel, have now fixed the final destination. The grand finale has begun. The first gap crossing of the grand finale occurs on April 26th, 2017 at 9 o'clock UTC. You are moving at approximately 31 kilometers per second relative to Saturn's cloud tops, faster than any prior Cassini orbit brought you, faster than the orbital velocities of the years of mission that came before. At this velocity, the 2,000 kilometer gap between the D-ring and the atmosphere is traversed in a little over a minute. The high-gain antenna is oriented forward to shield against any ring particles in the gap. Though models suggested the gap should be relatively clear, it had never been directly measured, and the particle environment inside the D-ring was genuinely unknown. You go through it alone. During the crossing, the antenna shields the spacecraft and blocks the communication link to Earth. You cannot transmit. The engineers watching the screens at JPL are watching a signal gap, 45 minutes of silence from the spacecraft they have been communicating with for nearly 20 years. Then the antenna rotates back to Earth, and the signal returns. The plasma wave instrument, which translates dust particle impacts into electrical signals that can be rendered as audio, recorded the crossing. The team had expected something like the sound of heavy rain, a dense continuous patter of impacts. What they hear instead when the recording is played back is a light drizzle. Sparse impacts. The gap is far cleaner than the most cautious pre-crossing models predicted. The gap is clear. The science return from the first grand finale orbit is extraordinary. The magnetometer, now measuring Saturn's magnetic field from just thousands of kilometers above the cloud tops, rather than the tens of thousands of the standard mission orbits, returns field values at an unprecedented spatial resolution. The result is immediately striking. Saturn's magnetic field is aligned with its rotation axis to within 0.06 degrees. Most planetary magnetic fields are tilted. Earth's magnetic axis is offset from its geographic axis by approximately 11 degrees, Jupiter's by about 10 degrees. Uranus's by 59 degrees. Saturn's is essentially 0. This is theoretically problematic. Standard dynamo theory, the physical model for how planetary magnetic fields are generated by convection and differential rotation in electrically conducting fluid interiors, predicts that a perfectly axially symmetric magnetic field cannot sustain itself. Some degree of asymmetry is required to drive the self-sustaining dynamo cycle. A field with zero tilt should decay over geological timescales, not persist for billions of years. And yet Saturn's field is there, strong, stable, nearly perfectly symmetric. After 13 years, the planet is still hiding something essential about itself. The INMS instrument, during close approach, samples Saturn's upper atmosphere directly, the first direct chemical measurement of Saturn's atmosphere by any instrument. The data shows methane, water, molecular hydrogen, and ammonia at the 1,000 to 1,500 kilometer altitude level, concentrations higher than pre-mission atmospheric models predicted. The excess water and oxygen compounds are coming from the rings above, charged ice particles following magnetic field lines down into Saturn's ionosphere, delivering ring material to the planet continuously. Saturn is consuming its own rings. The ring rain rate, the flux of ring material delivered to Saturn's atmosphere via magnetic field-guided particle transport, is measured at between 432 and 2,870 kilograms per second, depending on location and solar wind conditions. At the midpoint estimate, Saturn receives approximately 86 million kilograms of ring material per day. At that rate, over 100 to 300 million years, the rings will be gone. The rings that appear permanent from any telescope on Earth, the rings that have been there in every image, every observation, every human lifetime, are temporary. 300 million years ago, when the first dinosaurs were walking on Earth, the ring system that exists today may not have been there. Whatever collision or disruption created the current rings happened after complex life already walked the surface of this planet. The rings are younger than the bones of dinosaurs. The 22 grand finale orbits accumulate their measurements one by one. The ring mass is determined from the gravitational signature. The total mass of the rings is equivalent to approximately 40% of the mass of Mimas, one of Saturn's smaller moons, or roughly 2 Punxtensiger Denera kilograms. The rings are vast in area, extending from 66,900 to 483,000 kilometers from Saturn's center, but thin in mass. They contain less material than most of Saturn's moons, spread across an area larger than the distance from Earth to the Moon. They are thin and bright and temporary and beautiful. On September 11th, 2017, 4 days before the end, a final distant Titan encounter at 119,049 kilometers confirms the trajectory. The navigation calculation is correct. The path into Saturn's atmosphere is set to a precision of less than a kilometer at the cloud tops. On September 13th, you take the last images. The Imaging Science subsystem, 12 cameras covering wavelengths from ultraviolet through near-infrared, captures a final mosaic of Saturn's ring system. The C ring, the B ring, the Cassini division, the A ring, the faint outer F ring. The frames show the fine-scale structure that 13 years of imaging have revealed. Density waves launched by gravitational resonances with Mimas and Janus, sharp-edged moonlit gaps, the self-gravity wakes of the B ring that make it appear granular at small scales. The last image looks like any other image of Saturn's rings. It is not dramatic. It is not noticeably different from the first image taken in 2004. The instruments do not know it is the last one. The camera shutter closes for the final time at 15:15 UTC on September 13, 2017. The following hours are transmission. Every remaining kilobit of stored data, spectra, magnetometer readings, plasma measurements, dust impact records, flows outward at the speed of light toward the 70-meter dish at Goldstone, California, arriving 1 hour and 23 minutes after transmission. Everything stored, everything sent, everything received, and confirmed and archived. On September 14th, there is nothing left in Cassini's memory that has not been sent home. The mission scientists on the ground, who have spent careers analyzing Cassini data, know that after tomorrow there will be no new measurements, no new images, no new plume samples from Enceladus, no new Titan radar swaths. The last data has come in. In the early hours of September 15th, 2017, Cassini crosses the ring plane one final time, not through the gap, not shielded, but directly through the C ring itself. The plasma wave instrument records the impacts and translates them into sound. The recording sounds like crackling static on a radio tuned between stations, each pop a grain of ring ice, striking the antenna at relative speeds of tens of kilometers per second. You pass through the ring plane for the last time. Below, the upper atmosphere of Saturn is growing imperceptibly closer. The trajectory is fixed. The numbers have already decided everything that comes next. The thrusters are firing in small bursts, maintaining orientation, holding you steady in the correct attitude for the instruments to keep measuring, for the antenna to keep transmitting, for as long as the atmosphere will allow. Saturn waits, as it has always waited, patient, enormous, its rings turning in the long light of a diminished sun, its storms circling in their mathematical paths, its moons orbiting in their precise resonances, its hexagonal vortex rotating at the North Pole, its ocean moon broadcasting water into space, waiting for the small machine that has spent 13 years learning everything it could to come close enough that the air itself will catch it and hold it and not let go. The clock reads 5:45 UTC. September 15th, 2017. You are at approximately 1,915 kilometers above Saturn's 1 bar pressure level, the altitude defined as the nominal surface of the atmosphere, the point where atmospheric pressure equals 1 Earth atmosphere. At this altitude, the gas around you is so thin it barely qualifies as atmosphere in the conventional sense. The particle density is on the order of 10^6 molecules per cubic centimeter, a near vacuum that would be considered excellent conditions inside a laboratory vacuum chamber on Earth. But it is thickening. Not quickly, not in any way you would perceive if you were human and standing here, but the accelerometers, instruments that measure force applied to the spacecraft along all 3 axes, are beginning to register a number that was 0 for 20 years of spaceflight and is now, for the first time, not 0. Drag. The faintest, most imperceptible drag. Molecules of hydrogen and helium colliding with the spacecraft's exterior at relative velocities of 31 kilometers per second, each impact depositing a tiny increment of momentum, each molecule slowing you by an amount so small it would take billions of impacts to reduce your speed by a single meter per second. There are billions of impacts per second. The thrusters respond. 8 attitude control thrusters, each producing 1 Newton of thrust, firing in precisely timed sequences of milliseconds, push back against the torques that the asymmetric drag is beginning to impose on the spacecraft body. Cassini is not a perfect sphere. Its instruments, its high-gain antenna, its structural elements present different cross-sections to the oncoming flow depending on orientation. The drag is not equal on all sides. The thrusters correct for this. They have been correcting for perturbations of every kind for 20 years. Solar radiation pressure, gravitational tugs from distant moons, the faint push of Saturn's magnetosphere on the charged plasma surrounding the spacecraft. And they correct for this too, automatically, without intervention, precisely as programmed. You are still transmitting. The signal leaves the high-gain antenna at the speed of light, travels outward through the space between Saturn and Earth, a distance of 1.391 billion kilometers on this date, and arrives at the 70-meter dish antenna at the Canberra Deep Space Communication Complex in Australia 1 hour and 23 minutes after it was sent. In the control room at JPL, where a portion of the Cassini mission team has gathered, the signal being received right now was sent at 4:22 UTC, an hour and 23 minutes ago. They are watching what happened an hour ago. They will not know what is happening right now for another hour and 23 minutes. This is the final constraint of distance. In the early years of the mission, this communication delay was an operational challenge. Commands sent to the spacecraft took over an hour to arrive, and the spacecraft's responses took over an hour to return, making real-time control impossible. The mission was designed to accommodate this. Every major maneuver was pre-programmed and executed autonomously, with the ground team verifying results afterward. Cassini flew itself, navigated itself, managed its own anomalies within defined parameters. It is flying itself now. The atmospheric density at 1,500 kilometers altitude, you have descended 415 kilometers in the first 20 minutes of entry, is approximately 10 molecules per cubic centimeter, 10 times denser than at entry. Still a hard vacuum by Earth standards, still too thin to produce significant aerodynamic heating. But the accelerometers are reading a drag force that is now consistently above zero. The ENMS instrument is sampling continuously. At this altitude, 1,500 kilometers, the composition of Saturn's atmosphere is molecular hydrogen, H2, approximately 96% by volume, helium, He, approximately 3.25%, methane, CH4, approximately 0.45%, and trace quantities of ammonia, water vapor, phosphine, and complex hydrocarbons that the instrument is measuring in parts per million, resolving the chemical fingerprint of Saturn's upper atmosphere at a spatial resolution no remote observation could achieve. This data, gathered during the final minutes of the mission, will be the most direct chemical characterization of Saturn's atmosphere ever obtained. Published in the years following the mission's end, it will reveal that the abundance of heavy noble gases in Saturn's atmosphere is measurably different from Jupiter's, a constraint on the formation history of the two planets and the conditions in the early solar system that produced them. You are doing science. Even now, the altitude decreases, the density increases, the thrusters fire more frequently, correcting larger torques as the drag becomes more significant. At 1,000 kilometers altitude, approximately 40 minutes into the entry sequence, the atmospheric density has risen to the point where aerodynamic forces are becoming a meaningful fraction of the total force budget acting on the spacecraft. The temperature of the atmosphere at this altitude is approximately 540 Kelvin, hot by terrestrial standards, but not from aerodynamic heating. Saturn's upper thermosphere is intrinsically warm, heated by the absorption of ultraviolet radiation and by the dissipation of gravity waves propagating upward from the deep atmosphere below. The heat you register at 1,000 kilometers altitude is Saturn's own heat. The heat from entry friction has not yet begun. In, out. The thrusters are working harder. At 600 kilometers altitude, the atmospheric density, now approximately 10 milliohms per cubic centimeter, beginning to transition from the exosphere into the thermosphere. The attitude control system is firing thrusters in bursts that are longer and more frequent than any previous point in the mission. The aerodynamic torques are increasing non-linearly as the density rises. The thrusters are responding, but the margin between what they can compensate and what the atmosphere is imposing is narrowing. The magnetometer is reading. Saturn's magnetic field at this altitude, measured from directly inside the field's source region rather than from orbital distance, shows a structure more complex than the dipole field measured from above. Local field anomalies, small deviations from the smooth dipole geometry, appear at scales of hundreds of kilometers. These anomalies are generated by electrical current systems in Saturn's ionosphere, flowing along magnetic field lines and closing through the conducting layers of the upper atmosphere. The magnetometer team, scientists who have spent the full mission building a model of Saturn's field from the outside, are receiving measurements they never expected to have. Data from inside the source region, data that will require years to fully incorporate into the field models. Data that will still be generating new publications a decade after the mission ends. You transmit it all. Every measurement from every instrument encoded into the telemetry stream, sent outward at the speed of light toward the dish in Canberra that is tracking your signal with the slow, steady motion of its enormous reflector surface, compensating for Earth's rotation, maintaining the precise angular position that keeps the received signal at maximum strength. At 500 kilometers altitude, aerodynamic heating begins in earnest. The molecules of Saturn's atmosphere, hydrogen and helium primarily, but also methane and trace heavier gases, are striking the spacecraft's exterior at 31 kilometers per second. At this velocity, the kinetic energy of each collision is enormous. The leading surfaces of the spacecraft, the bottom face, the edges of the antenna, the exposed brackets and instruments on the lower structure, begin to heat. Not catastrophically, not immediately. The material temperatures are rising from their cruise values, maintained by heaters at around minus 20 degrees Celsius, upward through 0, through 100, through 200 degrees Celsius. The rate of temperature increase is accelerating as the density continues to rise. The thrusters are firing continuously now, not in discrete bursts, but in something approaching a continuous burn, small pulses overlapping, the attitude control system pushing back against an atmosphere that is pushing back harder with every kilometer of descent. The hydrazine fuel remaining in the tanks is being consumed at the highest rate of the entire mission. It will not last long. At 400 kilometers altitude, now more than an hour into the entry sequence, moving faster through the atmosphere as the trajectory steepens, the aerodynamic forces on the spacecraft exceed the maximum corrective torque the attitude control system can apply. The spacecraft begins to rotate. It is a slow rotation at first, barely perceptible in the attitude sensors. A fraction of a degree per second, the attitude control system recognizes it and responds, firing every available thruster at maximum duty cycle, trying to arrest the rotation and return the spacecraft to the correct orientation. For a few seconds, it succeeds. The rotation slows, the attitude stabilizes, the high-gain antenna swings back toward Earth, and the signal, which had wavered as the antenna moved off-axis, strengthens again. In the control room in Pasadena, the signal trace on the monitor steadies. Then the atmosphere pushes again. The density at 350 kilometers altitude is high enough that the aerodynamic torque on the asymmetric spacecraft body is beyond the capacity of any remaining thruster response to overcome. The rotation resumes, faster this time, and the thrusters firing at maximum cannot stop it. The spacecraft rotates. The high-gain antenna, 4 meters in diameter, designed to beam its signal toward the pinpoint of Earth across 1.4 billion kilometers of space, sweeps away from its target. The signal, which has traveled continuously from Cassini to Earth for nearly 20 years, weakens. At 11 hours, 55 minutes, and 46 seconds UTC, the signal from Cassini disappears from the receivers at Canberra. Not a clean cutoff, a fade, the carrier frequency shifting as the Doppler effect records the spacecraft's changing velocity during the tumble, the signal strength dropping as the antenna moves off-axis, then a threshold below which the receiver can no longer maintain lock. And then nothing. In the large room at JPL where the flight team has gathered, engineers who have worked on Cassini for 2 decades, scientists whose careers were built on its data, managers who have shepherded it through budget cycles and mission extensions, and the slow arithmetic of a fuel supply running down, no one speaks immediately. Then someone does. And the mission, 19 years, 335 days, and 17 hours after the engines of a Titan 4B rocket, ignited on a dark morning in Florida, is over. What is happening at Saturn at the moment the signal is lost is this. The spacecraft body is rotating in the upper atmosphere at increasing angular velocity, the aluminum and titanium structure heating on its leading surfaces, the thermal protection insufficient for what the atmosphere is now delivering. Within seconds of signal loss, the structural integrity of the spacecraft begins to fail, brackets deform, electronics housing cracks, components that have functioned without interruption for 20 years begin to break apart. Within minutes, Cassini is no longer a spacecraft. It is a cloud of metallic and ceramic and electronic debris, each fragment following its own ballistic trajectory into the deeper atmosphere, each one heating and ablating as it descends, each one eventually vaporizing into atoms and molecules that mix with Saturn's own hydrogen and helium and methane. The atoms that made up Cassini, the aluminum of its structural frame, the titanium of its propellant tanks, the silicon of its electronics, the carbon of its thermal insulation, settle into Saturn's atmosphere, molecule by molecule, becoming indistinguishable from the planet itself. The machine that studied Saturn for 13 years has become part of Saturn. It is inside the planet now. What remains is not the spacecraft. What remains is everything it sent home. 4,324 scientific papers, as of the count made several years after mission end, a number that continues to grow as scientists work through the archived datasets that have not yet been fully analyzed. The confirmation of a global liquid water ocean beneath the ice of Enceladus. The detection of molecular hydrogen in the Enceladus plume, indicating active hydrothermal chemistry at the seafloor. The silica nanoparticle measurement that placed the hydrothermal temperature above 90 degrees Celsius, the first direct chemical sampling of Saturn's upper atmosphere, the measurement of the ring mass and the ring rain rate, the age constraint on the rings, the mapping of 67% of Titan's surface, the characterization of its lakes and dune fields, the identification of the Selk crater as a target for future prebiotic chemistry investigation, the resolution of the North Polar hexagon through a full seasonal cycle, a decade of magnetic field measurements that revealed Saturn's near-perfectly axisymmetric dynamo, still unexplained, still generating debate, still the subject of theoretical work that has not yet converged on an answer. The 453,048 images. None of these things existed before Cassini. The knowledge did not exist. The data did not exist. The questions, the specific, grounded, scientifically precise questions that the mission raised and could not answer, did not exist in their current form. They were vague before, they are now specific. They have numbers attached to them, they have locations. Is there life in the ocean of Enceladus? The question is no longer, might there be an ocean on Enceladus? That question is answered. The ocean is there. The hydrothermal vents are there. The organic chemistry is there. The energy source is there. The question has moved, sharpened by Cassini's measurements, into a form that a future mission can be designed to address. That mission is called ORCA, the Ocean Worlds Life Surveyor concept, one of several Enceladus mission proposals under various stages of development in the years after Cassini's end. It would carry a mass spectrometer orders of magnitude more sensitive than INMS, capable of detecting individual organic molecules in single plume particles, capable of distinguishing the biosignatures of biological chemistry from the products of abiotic hydrothermal reactions. Dragonfly will go to Titan. A successor will eventually go to Enceladus. And somewhere in the preparation for those missions, in the laboratory calibrations, in the instrument design documents, in the trajectory calculations, Cassini's data is the foundation. The numbers come from Cassini. The locations come from Cassini. The knowledge of what conditions to expect, what instruments to prioritize, what questions to ask, all of it traces back to a machine launched in 1997 that spent 7 years traveling to Saturn and 13 years studying it before falling into the planet it had watched for so long. In, out. The rings of Saturn are visible tonight from anywhere on Earth with a small telescope. You need only point it at the correct part of the sky. Saturn moves slowly through the constellations, completing one orbit of the Sun every 29.4 years, so it is visible in a predictable region for months at a time. Through a telescope with a 70mm aperture and sufficient magnification, the rings resolve clearly from the disk of the planet, the A ring bright at the outer edge, the Cassini division visible as a darker gap, the B ring broad and brilliant, the shadow of the planet curving across the ring system on one side. You can see it tonight. What you see through that telescope is the same ring system that Cassini spent 13 years measuring from inside. The same ice particles, predominantly water ice, now you know that. Now it has been measured, that Cassini flew through during the grand finale crossings, that impacted the plasma wave antenna at kilometers per second and were translated into the crackling sound of static. The same material that is raining at hundreds of kilograms per second down magnetic field lines into Saturn's ionosphere. The same rings that are temporary. That will be gone on geological timescales, while something still lives on Earth to look up and notice they are missing. You are looking at something that will not always be there. And somewhere beneath the ice of a small white moon orbiting inside those rings, a moon you cannot resolve through a backyard telescope, a moon that requires the cameras of a spacecraft to see clearly, there is an ocean. There are hydrothermal vents at its floor. There is warm, salty, alkaline water circulating through fractured rock, producing hydrogen gas through the same chemistry that feeds life in Earth's darkest ocean. Whether something is living in that water is a question that cannot be answered from here. It can only be answered by going there. Cassini went, and Cassini told us what it found, right up until the moment it could no longer transmit, right up until the atmosphere of Saturn closed around it, and the signal, which had traveled 1.4 billion kilometers to reach the ears of the people listening, fell silent. The silence in the control room lasted a moment. Then someone began to talk about the data, about what had been received, about what it meant, about what would need to be done next, about the papers to be written, the missions to be proposed, the questions to be answered, because that is what the data is for. Not for keeping, for using. The rings are turning tonight. They have been turning since before the first human looked up at a dark sky and wondered what the points of light were. They will continue turning long after the last person who remembers Cassini is gone. They will turn for another 100 million years, slowly thinning, slowly raining into the planet below, until one day, far in the future, in a solar system that will look essentially the same from a distance, but will have lost this particular feature, the rings are gone. And Saturn will be there, enormous, golden, banded, stormed, its hexagonal vortex rotating at the North Pole, its moons in their precise orbits, Enceladus still broadcasting water into space, just without the rings. For now, they are here. For now, a small white moon is broadcasting water into space. For now, somewhere in the data archives of a space agency on the third planet from the Sun, the measurements of a machine that fell into a gas giant are still being read, still generating new understanding, still answering questions and raising new ones. You can rest now. The data is safe. The science continues. Enceladus is out there, and it is warm inside. Let the rings turn. Let the distance be enormous and the science be real. Let the questions be large enough to matter and patient enough to wait. You have traveled far enough for one night. Somewhere between here and Saturn, across 1.4 billion kilometers of space, the rings are catching sunlight, as they always have, as they will for millions of years to come. Everything you heard tonight is real. Cassini is out there, Not as a machine, not anymore, but as part of the planet it spent so long trying to understand. If this story stayed with you tonight, a like and a subscription means the world to this channel, and a notification bell means the next journey finds you here. Good night. Sleep well, and drift gently into the universe.